We've been dealing with radical functions for a while now, and we're going to focus on two of them in particular and discuss how to graph them. We're going to be graphing the square root function and the cube root function. So here's what the parent function of the square root function is. Y equals the square root of x. And here's how that graph looks. Notice a couple things, that it first looks like a parabola on its side cut in half. If we were to draw that, that's the parabola sideways, but the square root function is half of that. Also look at the domain and range. The domain of the parent function is x is greater than or equal to 0, and that should make sense because we can't take the square root of a negative number, so our domain has to be 0 or larger. Now, obviously, once we start shifting our graphs left and right, the domain will change dependent on that. But remember, we cannot take the square root of a negative number, which is why our domain is going to be changing. Up until now, the domain of all the functions we've talked about has been negative infinity, comma infinity. This is the first one with a different domain. Our range. We've talked about functions with ranges that are not negative infinity, comma infinity, or all real numbers. The range is going to be greater than or equal to 0. And again, because we can't take the square root of a number and have the result or the y value be negative. And just like with other shifting, once we start shifting our graphs up and down, that will change as well. When we graph radical functions, we're going to have a table, an xy table, and all square root functions are going to start with these 3 points. Oops. So we're always going to graph, these 4 points. We're always going to graph these 4 points at first, and then we're going to transform them based on A, H, and K. A, H, and K have returned, and they do the same thing as they've always done. A is that vertical shrink or stretch, depending if A is larger than 1 or smaller than 1, or if we have a reflection, if A is negative. H is going to be our horizontal shift, moving left or right, the opposite of what you see. K is our vertical shift, going up or down, and it's exactly what you would see. So that's why we really stressed earlier in the year the importance of knowing what A, H, and K do. So we're going to graph y equals negative 2 times the square root of x. We're going to start with the table that we just wrote down up above. 0, 0, 1, 1, 4, 2, and 9, 3. Now we're going to add a third row, and in this third row, we're going to label it negative 2y. The reason we're labeling it negative 2y is because our a value is negative 2. So whatever your a value is, that's what that third row is going to be. Now we're going to multiply all of our y values by negative 2. So 0 times negative 2 is 0. 1 times negative 2 is negative 2. 2 times negative 2 is negative 4. And 3 times negative 2 is 6. Now we're going to ignore this middle row, and we're going to plot 0, 0, 1, negative 2, 4, negative 4, and 9, negative 6. So our graph will look like that. So now our domain and range. Well, our domain and range is always going to be dependent on the starting point right here. And in this case, it is 0, 0. Domain is going to be 0, infinity. And our range, since the y values are going down, they're eventually going to go all the way down to negative infinity. It's going to go down very slowly, but eventually it will get there. So the range is negative infinity, 0. And ever we're asked to compare, that's when we do our ST. Because A is negative, we have a reflection over the x-axis. Because that number in front is 2, we have a vertical stretch. And we don't have an h or k plus or minus anything, adding and subtracting anywhere. So there is none when it comes to the none when it comes to the translation. So it's not that terrible of a process. You just have to remember to do all of the steps. We are actually going to continue on. After we do all the square root ones, then we'll come back and do cube root functions. So we'll go to this example right here. Now you say, well, this doesn't look like a square root function. Remember, the 1/2 power is the same thing as a square root. So you can think of this as y equals -2 times the square root of x plus 2, and then plus 3 on the outside. So this looks just like what we did before, except now we have an h value of plus 2 and a k value of plus 3. What that does is that plus 2 means we're going to be moving left 2, and that plus 3 on the outside means we're moving up 3. Now we're going to do the exact same process that we just did. An xy table, 0, 0, 1, 1, 4, 2, 9, 3. And we'll do that third row. -2y, again, because our a value is -2. So 0, -2, -4, -6. Because we're multiplying, the reason why we're writing -2y is you're taking the y values from above and multiplying them all by -2. So let's cross off this right here. All right, so we're going to plot those points, 0, 0, 1, -2, 4, -4, 9, -6. There. So you may be saying, well, that looks exactly like what we did above. What about that translation, left 2, up 3? Well, the way I like to do that is once I have this done, I like to take each of these points and move them left 2 and then up 3. So on this point, left 2, up 3. This is not the only way to do it. 2, 3. So again, each one of these points, I moved left 2 and up 3, and then I can connect them like that. You could write out the points instead of counting. You could take 0, 0 and say, okay, if I move left 2 and up 3, that's going to be -2, 3. And then take 1, -2, and say, okay, if we move left 2, that's -1, and up 3 is 1. You could do it that way for all the points if you wanted to. I just think that once you start getting some fractions, it will be a little bit more difficult. So now for domain and range, we want to use this light blue graph, or this light blue line, and our starting point is -2, 3 right here. So now my domain and range is going to be reliant on that. Domain, x values, is going to be -2, infinity, because our x values start at -2 and they keep going to the right. The range, those are your y values. Our y values are still going down to -infinity here, but they're going to go up to +3. And this question did not ask us to compare, so we're going to leave it like this. Now with cube root functions, we have y equals the cube root of x, and these functions look like a weird looking S. One of the things about cube root functions is that the domain and range is always all real numbers, or -infinity, infinity. The process of graphing cube root functions is going to be exactly the same as graphing square root functions. The only difference or only two differences is one, the domain and range. The domain and range of cube root will always be -infinity, infinity, whereas square roots changed based off of your h and k value. But the table is also different. The table that we're always going to use is -8, -2, -1, -1, 0, 0, 1, 1, and 8, 2. So when we graph these, we're going to use this table, but still make that third row and multiply all the y values by a. And just like with the square roots, we have our h and k, and that will move our graph left and right and up and down after we graph the third row here that we're going to add. So let's now look at a cube root function. We have 1/2 times the cube root of x. Say the domain and range and compare it. So like I was saying, the cube root table looks like this. And then we're going to add a third row. And in that third row, we're going to multiply all the y values by our a value, which is 1/2. So we're going to have 1/2 y. So -2 times 1/2 is -1. -1 times 1/2 is -1/2. 0 times anything is 0. 1 times 1/2 is 1/2. And 2 times 1/2 is 1. So we will plot -8, -1. -1, -1/2, 0, 0, 1, 1/2, and 8, 1. So our cube root graph will look like this. Domain and range, like I said earlier, domain and range for cube root is always -infinity, infinity, always. And it did ask us to compare, so we have r, s, t. Because our a value is positive, there is no reflection. But because it numbers 1/2, we have a vertical shrink. We don't have an h and k. We're not adding or subtracting anything inside the radical or outside the radical, so there is no translation. So once you get used to the idea of this third row and then translating that graph, both of these functions become a lot easier. You're just going to have to remember the table we use for each one. All right, so let's go down and look at example 4 here. This is a cube root function, just like the one above. And with this one, as the same a values, the table is going to look the same, but we have, an h and a k. So let's start with our table. Remember, all cube root functions will start this way. And then we'll have that third row here, where we multiply everything by that a value of 1/2. So we have 1/2 y. So -1. We have -1/2, 0, 1/2. Whoops, I got these mixed up. And 1. And then we'll ignore this row and graph our points. -8, -1, and then 8. So this is our graph before the translation. Now our translation, since it says -1, we're going to move every point right 1 and up 2. So right 1 and up 2. Right 1, up 2. 2. Right 1, up 2. Right 1 and up 2. So that's what our graph will look like. Every point moved right 1 and up 2. And our domain and range, because it is a cube root, is -infinity, infinity for both. All right, so now let's look at this one here. I'm going to convert this to a cube root, and then I'm going to have you guys pause the video and try it. So because it's a 1/3 power, it's going to be the cube root of x plus 1 minus 3. So you're going to graph it like that. So go ahead and do this, pause the video, and once you're done, you can unpause it and check. All right, so go ahead and check your work with mine. Again, the domain and range for both of these will be -infinity, infinity. So I multiplied all the y values in that table by -3. And then I applied those in purple, and then I moved each point left 1 and down 3 and got my green graph. So in this example, it says biologists have found that the shoulder height, age in centimeters of an elephant can be modeled by that equation, where t is the elephant's age in years. Use a graphing calculator to graph the model and draw the sketch below. So in our calculator, if we go to y equals, we're going to do 62.5 times the third root, so times 3. Then we hit the math button and go down to the fifth option, third root of x. Make sure you press the right arrow key, plus 75.8. And now we graph that. Now the graph is going to go off our normal screen a little bit, and that should make sense because, look, we have a k value of 75.8, and if we take a peek at letter B, we want the y max to be at least 200, so let's go 250. So if we press the trace button, we can see when the y value gets to 200, it's about 7.87 when the y is 200, so that's about 8 years. So it's about 8 years. In that sketch, it looks like a normal cube root function. Start at 0, 0. If we wanted to be a little bit exact, we have a point 1, 138. If we go up by maybe 50s, each tick mark is 50, every 2 tick marks is 50. That'll make it easier to work with. And notice I didn't go for the negative direction. That's because we're talking about years for an elephant, and that just doesn't make sense to have negative years. The last one, create a square root function where there is a vertical shrink or reflection across the x-axis and a starting point in quadrant 3. Identify the domain and range. So y equals, we want a vertical shrink and a reflection across the x-axis. So let's go like -2/3. X. Now quadrant 3, if you have forgotten, 1, 2, 3, is in the lower left, where x and y are negative. So we need to plus a number and then minus a number on the outside. So then your domain for this one would be -7, infinity, and your range would be -9, negative infinity, comma -9, because we have that reflection over the axis. All right, so that's it for graphing square root and cube root functions. Make sure to like the video and subscribe.